as a result of refraction of light, the change in the apparent position of objects. Okay, so that is what we are coming to look at it. Okay, if I have a cup of water, then I have an object placed within or at the bottom. Because the light traveling from the object, okay, to the observer, the light is always coming from a denser medium into a less dense medium. There will certainly be deviation of the light. So we are going to look at how an observer will perceive this. The object is here. This is water. This is the object. The real depth is actually from here to where the object is. This is the real depth. Okay, dr. Now, whenever light we see as a result of reflection of light from the object into our eyes. So you can, for you to see this, light must come from the object into our eyes. So we are looking at light coming from two different ways. So when the path of light is such that it is perpendicular to this boundary, it is perpendicular to the surface of the water, the path goes undeviated. So it would go undeviated. So long as the path of the light is perpendicular to it, it will go undeviated. Then let's also consider light moving at an angle. Let's draw a normal to the surface. Now, over here, we are considering this to be an angle I. Here, because the path of light is traveling from water to air, when it gets to the boundary, will it deviate towards the normal or away from the normal? Yes. Will the path deviate towards the normal or away from the normal? Yes, class, I'm waiting for feedback.
Away from the normal.
So this is how it will deviate, away from the normal, because the light is coming from a denser medium into a less dense medium. Okay. Now, when we trace back the path of the reflected or refracted ray, where it meets this other ray, that is where the image will be formed. So if an observer is here, the observer here sees the image of this object to be here. Optical illusion. This is the angle of incidence, and so this will be the angle of refraction R. Please, are we okay? Are we fine?
Mr. Ada, please, could you go over again?
Okay, I'm going over for the second time. So let's clear this. We have an object placed in a cup of water. We have a coin. Matilda, are you there? Matilda.
Yes, Mr. John.
Hey, so you are in town. We have an object here. Okay, the cup has water. Now, we want to, once the object is placed in a cup containing water, when you are looking at it, okay, there will be optical illusion. Akofala, your topic, optical illusion, meaning that what you see may deceive you. So you see the object, okay, behaving as if it's been moved forward, but in actual fact, that is not what it is. Now, to an observer who is here watching or here, light, once this is the object and you are watching, then it means light would have to travel from the object to the observer. But when the path of light is perpendicular to the interface, the boundary between air and water, when the light path is perpendicular, the path goes undeviated. So long as this ray is perpendicular to the boundary, it will never be deviated. So that is one ray. Don't forget, we need at least two refracted rays to meet or appear to meet to give us an image position. So we have one, we need another. Now we are looking at a ray at an angle. So when the ray, okay, is at an angle I from the object, let's draw this, the normal. The moment this incident ray from the object hits the glass air boundary, the light from the object is moving from denser medium into a less dense medium. And so the path of this ray will be deviated away from the normal. Okay, now, where two or more refracted rays actually meet, a real image will be formed there. But look at this ray, look at this ray. There is no way they will meet. There is no way they will meet in front. Hence, we have to retrace the path of the refracted ray. And where it appears to meet the other refracted ray, the image is formed there. Okay, what we see is virtual or an illusion, because you see, this image is formed as a result of the retracing of the two paths. So whenever we retrace the path of refracted ray or reflected ray, the image will be virtual. Please, are we okay? Are we okay? So that's the more reason why this image would be a virtual illusion. Okay, so when an observer is here and watching the object, this is where he sees the object. Okay, so it means that from the surface of the water to where the object is the real depth, dr. From where the object is, from the surface, okay, to where the image is the apparent depth. Okay, now once this is I, this is R, angle of refraction. Angle of refraction. Okay, this angle would correspond with this angle. So if this is R, this is also R by corresponding angles. So let's do something. We have this point, and this point. Let's label this as O, A, B, C. Okay, so we have labeled the path. Now, Now we have two different triangles within. Considering triangle BCA, BCA, the smaller triangle. When we consider the sine of R, this is equal to the opposite, which is AC over the hypotenuse AB or BA. So sine of R is equal to opposite ACA or AC over the hypotenuse, which is AB or BA. Are we okay? Are we okay here? Then,
Miss Edia, please go over that part real quick. Naming
Okay.
where the sign is.
you see, this is the refracted ray. And so the angle between the refracted ray and the normal is the angle of refraction. Okay. Now, if this is R, when you extend this, then it means this angle would also be R by corresponding angles. Okay, when this is perpendicular, this is perpendicular. And this is the same line, the extended version. If this is R, this will also be R. Are you fine?
Yes, please.
Good. So when we take the sine of this angle, sine R, it will be equal to opposite CA or AC over the hypotenuse AB or BE. And that's what I've done here.
Miss Adia, please, my question is, why are we taking the angle of incidence from the normal by the coin and not by the point A?
You see, because the light, okay, the light is coming from the object and is going here. This is where, when it gets to the interface, this is where it is deviated. So this angle, this ray becomes the angle of refraction. It's because we are moving from water to air. That is why we are taking this as I and this as R. Are you okay?
Yes, please.
In actual fact, it can also be seen the other way around. We can see it to be coming from air to water, but in reality, if you are here and you are observing, the light would have to come from the object. So it will be air, water to air. Okay.
Yes, please. Thank you.
Good. So let's also find sine I. Sine I. With sine I, then we are considering triangle, the bigger triangle, OCA. OCA. When you consider the bigger triangle, OCA, then sine of I would have to be equal to the opposite, which is still AC or CA over the hypotenuse, which is OA. So this side over this side will be equal to sine of I. Please, are we fine?
No, really, please, Miss Adia.
Yes, please.
Triangle OCA, this bigger triangle. If you find the sine of the angle of incidence I, okay, sine I is opposite, which is CA over hypotenuse, which is OA.
Yes, please.
Are you okay?
Yes, please.
All right. Now, the consideration for this, I want to change my marker. whenever we are doing this, we consider at normal incidence. What does it mean? Normal incidence means that we are considering small angles of incidence. And this small angle of incidence would equally give us small angle of refraction. So at normal incidence, I'm coming. I want to change the marker. So at normal incidence, and what do I mean by normal incidence? Normal incidence means that we are considering small angles of incidence, small angle of incidence basically that, because whenever we consider small angle of incidence, it will give us small angle of refraction. So at normal incidence, sine of I is approximately equal to the tan of I. Okay, approximation. These are conditions to this. At normal incidence, where the angle of incidence is chosen to be very, very small, then this sine I would have to be equal to tan I. And sine R would have to be approximately equal to tan of R. So this would have to be equal to tan R at normal incidence. So if sine R is equal to tan I, from the same triangle BCA, let's look for tan R. Tan of this angle. Tan is actually, tan R will be opposite, which is CA or AC over the adjacent, which is BC over BC. And tan I, tan of this will be equal to the opposite, which is still AC or CA over CO.
Mr. Dia,
Hello.
please, why are we using tan?
I've given you a condition, and the condition is that when you pick small angles of incidence and small angles of refraction, sine I is approximately equal to tan I, and sine R is approximately equal to tan R. So that's the reason for which we are considering small angle of incidence, normal incidence. So that's the reason for which sine changes to tan.
Mr. Dia, please, does it mean that like the value of I at that instance would be very, very small?
Exactly. That's what I mean. Okay.
Thank
These considerations are taken on conditions. We consider small angles for lenses, reflection, refraction. We consider small angles for our theory. Okay. So that's why we are considering sine I changing to all that at normal incidence. Yes, Akofana.
you.
Mr. Dia,
Please, I can't see the other parts of the book.
I think I've adjusted it a bit. Akofana, go ahead.
Mr. Dia, please, I would like to know how small is small, as in smaller than 45, or is there a
No,
range?
very, very small. There's no range. There's no specific value. At small angles of incidence, there's no specific value for now. All right. All that we are saying is that in considering small angles of incidence, is that okay?
Okay.
All right. Now, if this is it, then if we take the refractive index, absolute refractive index, this has to be equal to, this would have to be equal to sine I over sine R. So in actual fact, this is also equal to tan I over tan R for absolute refractive index. So it means that N would have to be equal to, let's substitute our values for tan I and tan R. Tan I is equal to AC over CO all over sine R, which is tan R, and tan R is AC over BC. The refractive index, which here we are considering absolutes, is equal to AC over CO times BC over AC. Are we fine here? Please, are we okay? All that we are saying is that we are applying
Yes,
whatever we. Hello. I'm going over. So all that we are saying is that we've now had expression for sine I and sine R, which is equal to tan I and tan R. We are applying it to refractive index. Refractive index is equal to sine I over sine R. And so I'm only substituting the values of sine I and sine R, which is also equal to tan I and tan R. So I'm only doing substituting or substitution. Tan I is this. This is tan I. AC over CO. Okay, AC over CO. And tan R is AC over BC. So I'm only substituting whatever we've derived before. Please, is that okay? Are we okay?
Mr. Dear,
Hello.
please, which angles are you calling small angles?
Small angle of incidence. So we are considering I to be very, very small. But the fact is that if I is very, very small, you will get a corresponding small angles of R automatically. So if I is small, R will certainly be small. Okay.
Yes, please.
So when you take this ratio, AC would cancel out. Therefore, refractive index will be equal to BC over CO. Now, what we are considering is absolute refractive index. Akofala.
Mr. Dear, please, I'm looking at the tan I. Doesn't mean it disobeys the rule.
Tan I.
Yes, please.
No, tan I from here is opposite AC over B over CO. It is not disobeying anything. But no, I understand your question. I'll come to it.
Okay.
Okay. So from what we have done, you see, the absolute refractive index N is equal to BC over CO. But from what we are doing, this is not absolute refractive index. This is the refractive index from water to air. But what we have considered is actually from air to water. Okay, so we want to adjust this so that it will conform with what the direction of the light from water to air, not the other way around. But we know that the refractive index from air to water is always equal to 1 over the refractive index from water to air. Okay, so if we make N from water to air the subject, it will be equal to 1 over the refractive index from air to water. Now, this is what we got for absolute refractive index. So it means that to get it from water to air, the refractive index from water to air, which we actually have, then it will be equal to 1 over BC over CO. And this will be equal to CO over BC for the refractive index from water into air. Okay.
No.
Please. This is what I'm
Mistake.
saying. Yeah,
Please, how come the first N is rather absolute refractive index?
You see, we are looking at the general formula for absolute. This is absolute refractive index, sine I over sine R from Snell's law. From Snell's law. And this is from air to water. This we have BC over CO. Okay. And don't forget, from what we are doing, it isn't absolute. This is, once the light is from water to air, then we have to have it as WA instead. Okay.
What I mean is that it's from the water, the air.
Come again.
So you see, please,
I get you. This must be from water to air. This must be from water to air by our angles. Okay. This, what we have, must be from water to air by our angles. This is I over R. So this must actually be from water to air. Please, are you okay? Hello? Let me take that part again. It's actually here. From what we have, we are looking at the light moving from water to air. So if we take N is equal to sine I over sine R, what is the path? We are moving from water to air. So this is actually the refractive index of air with respect to water. Okay. This is the refractive index of air with respect to water, and it is equal to sine I over sine R, which we substituted tan I AC over CO, all divided by sine R, which is, I'm coming, let me clear this from the screen. Tan R, which is AC over BC. Therefore, the refractive index from water to air is equal to AC over CO times BC over AC. This and this will cancel, so we have BC over CO. Now, because this ratio, we are taking this angle over this angle, this is the refractive index of air with respect to water. Please, are we okay? Akovala, are you okay?
Yes, please.
Good. Now, we are interested in expressing this rather as absolute. So we want to have it as from rather air to water. But where is the duster?
Why?
Because we always want to express refractive index in terms of absolute. Okay, absolute. That is why we want to actually reverse from water to air to water, because the refractive index of a material is always in absolute terms. Okay, so refractive index from water to air, we know is equal to 1 over the refractive index from air to water. So if water to air is equal to BC, then it means that the refractive index from air to water would be equal to CO over BC. It's just the inverse of whatever we got here. Please, are we fine? I'll go over. But do you follow this part?
Yes, please.
Hello? Good. We are just interested in absolute. That's why we are reversing it from water to air to water. So that will be the inverse of this thing. Instead of BC over CO, we'll have CO over BC. Now, let's look at what we have. What is CO? CO is the real debt. Real debt. Over, this is BC. BC is the apparent debt. So the absolute refractive index of an object giving you an illusion, okay, can always be determined by its real debt divided by its apparent debt. And this is the concept we were trying to look at or derive all the while. The absolute refractive index of an object placed, okay, in a denser medium being viewed from up is always equal to its real debt over its apparent debt. Now, what is the extent to which the object has been displaced? This is the real position of the object. Okay, please, the height, the depth is always measured from the top of the water, from the surface of the water to where the object is. So this is real, the dr, and this is apparent debt dA. We call the distance from the original position of the object to its new position as the normal displacement or vertical displacement d. So we realize that the apparent debt, the real debt r is equal to the displacement plus the apparent debt a. So r is equal to d plus a. Okay. If we make d the subject, d is equal to r minus a. So we are saying that this vertical displacement is equal to the real debt minus the apparent debt. Okay. This one, we can give it an expression. What is real debt? Real debt is OC. So OC minus, what is the apparent debt? The apparent debt is BC. Okay. When we talk, hello.
So sorry, but please, I'm lost from the r is equal to d plus a.
This is the real debt from O, the position of the object, to the surface of the river or of the water is the real debt, R. So we are using R for the real debt. And then the apparent debt is from the surface of the water to the new position of the object, A. So R is equal to A plus the vertical displacement D. Is that okay? So please, you have to define it. Where R is equal to the real debt, then A is equal to the apparent debt, and D is equal to the vertical displacement, or sometimes called as the normal displacement. So when you make D the subject from the relation, it means that the vertical displacement D is equal to R minus A. Please, are you okay? Are you okay?
Yes, please.
Okay. If let's clear the whole thing and quickly go over for the understanding of all. Okay. Please, if you are writing, quickly do so we could continue or look at it all over again. Do I clean it? Do I clean the board? Okay. So we have an object, okay, dropped in a cup of water. The object is being observed by an observer, okay, looking at it here. Okay. Now, yes, there can be a lot of light or rays, light rays coming from the object. So a ray of light going perpendicular to the surface goes undeviated. The reason is that the ray is perpendicular to the surface. So it goes undeviated. We have another ray acting at an angle. Okay. So when the ray hits the boundary air to water interface, it will deviate away from this normal. So this is a refracted ray. This is the angle of incidence I from the object. Meaning we are still considering, because this is perpendicular to the surface, this also behaves like the normal. Okay. And this gives us the angle of refraction, R. When we extend the path of the refracted ray, where it meets the other ray, the image of this is there. We are labeling this vertices A, B, C, and this is D. Okay. Once this is R, this is also R.